Okay, pH titration curves. pH titration curves. Okay, this is just a way to monitor a titration carefully, slowly and carefully. So you monitor a titration carefully. Okay, so let's just draw first what a titration curve would look like. So you've got your axes. Okay, so on this axis you've got pH. So I'm just going to divide it up approximately pH 1, pH 2, 3, 4, 5, 6, 7, all the way up to 8, 9, I'm going up room, 10, 11, 12, 13, and then up to 14. Okay, so you've got pH along that axis. Now when you're doing a titration, so you've got your conical flask. So let's say you've got some acid in your conical flask. Let's pretend you've got 25 centimeters cubed of 0.1 mole per decimeter cubed hydrochloric acid. Pretend that is in your conical flask. And then you've got your burette. And in your burette you have got 0.1 moles per decimeter cubed sodium hydroxide, and you're doing a titration, but you are not putting an indicator in. There's no indicator. So how can you tell when the titration has finished? How can you tell when neutralization has happened if there's no indicator? So instead you put a pH meter. So just put a pH meter inside your conical flask. So as you're dripping down the sodium hydroxide, you'll neutralize, the pH meter will monitor the titration. Okay, right, so if the pH meter is in there originally at the start it's hydrochloric acid, so it'll be about pH 1, pH 2, something like that. The bottom axis is because as the titration is happening, we're going to add sodium hydroxide. So this bottom axis is going to be volume of the 0.1 concentration moles per decimeter cubed sodium hydroxide added. Okay, so this is a simple example. If you've got 25 centimeters cubed of 0.1 moles per decimeter cubed, and you've got of HCl, and you've got the same concentration of sodium hydroxide, at what point will neutralization happen? It will happen when 25 centimeter cubed of this sodium hydroxide has been added. So first thing you do when you're sketching a titration curve, so you can do the experiment, get the results, and plot a titration curve. But you will be asked in an exam to sketch a rough sketch of a titration curve. So you work out where the starting pH will be, depending on which acid is used. You work out the neutralization point. It'll be when 25 centimeters cubed of sodium hydroxide has been added. And because sodium hydroxide is a strong base, then you'll finish somewhere up pH 13, somewhere up here. Okay, so what happens is, as you gradually drip in the sodium hydroxide and you measure the pH. Now there's a lot of acid in here, so the pH doesn't change much initially. It's not horizontal. It very slightly, ever so slightly, kind of increases, just really slightly. But then when you get to 25 centimeters cubed, one drop of sodium hydroxide and neutralization will have happened. So the pH increases considerably. We call it the vertical section, and then go like that. Okay, so what you've got here is you've got an excess of acid here. Okay, so this is you've got excess of acid, and so the pH is just gradually, just very slightly, then one drop and neutralization happens, and the pH will increase rapidly, and then you've just got your sodium hydroxide. Okay, and this is an excess of base over here. Excess of base. Right, and then the vertical section, we call this the vertical section of the pH curve. The vertical section of the pH curve. And if you take the midpoint, so I'm just guessing, it's just a sketch, I'm just guessing. If you take the midpoint, then that is called the equivalence point. Okay, so the center, the midpoint, is called the equivalence point. The center is called the equivalence point. And what does that mean? The equivalence point is when the volume of one solution, that exactly reacts with the volume of the other solution. With the volume of other solution. Okay, so it's when the volume of one solution exactly reacts with the volume of the other solution. That's the equivalence point. Right, now, if you imagine we were doing this the other way around. So let's just take a pH again. But say, for example, this time in the conical flask, you've got the base, you've got the 0.1 mole per decimeter cubed sodium hydroxide. Okay, then the starting point would be about pH 13. That's where you would start. Again, if it was 25 centimeters cubed, it would neutralize at 25 centimeters cubed. If in your burette you had the acid in your burette, then it would end somewhere down pH 1, and you had your pH meter in, then the titration curve would be the other way around. So you would go, sorry, I'm not doing this great, that's it, and then you come down to 25, then you drop considerably, and then you would go along like that. Okay, so you've got to be able to be flexible. You've got to check what's in the conical flask. That's your starting point. And then when you are dripping in the sodium, what's your finish point, okay? And then the midpoint is called the equivalence point. So unlike normal titrations, acid-based titrations, you're not using an indicator, you're just monitoring with pH. And you go way past, so what we're doing is we're going way past the neutralization point. And we are adding probably about 50 centimeters cubed of acid. So this is the volume of acid added. Volume of acid added in centimeters cubed. So we're going way past, because normally you stop at titration. One drop and you stop at titration. But this is just monitoring it carefully and going way past and adding more than what you need. Okay? So this is what a titration curve is. Let's talk a bit about acid-base indicators. This is for acid-base indicators. Right? So what actually is an acid-base indicator? Now, you do not need to know the formula of any indicators. What you need, because they're quite complicated, what you need is to know that an indicator is a weak acid, is what you need to know. An indicator is a weak acid. So if you take remember a weak acid partially dissociates into ions. Okay, so if you take methyl orange, for example, indicator methyl orange, which is quite a big complicated molecule, then methyl orange, when it's in this form, it's the color red. When it's in the HA form, when it's in the conjugate base, it's the color yellow. Okay, and therefore at the end point, now the end point, when we say end point, what it actually really means, the end point of a titration, what it means is when the concentration of the acid equals the concentration of the conjugate base. That's the end point of the titration, and therefore the color that you see at the end point is in between the two extremes, the two colors. So in this example, if red is when it's in the acid form and yellow when it's in the conjugate base form, the end point will be in orange, will be the end point. So that's the end point of the titration. It's when those two colors, the mixture of the two colors. Okay, it's a weak acid, right? So if the indicator is in acid, then the position of equilibrium will move to the right. So in acid solution, the indicator will be the color red. Okay, so in acidic solution, when there's acid there, the position, Le Chatelier's principle, the position of equilibrium will move to the left. Position of equilibrium moves to the left, and the indicator will be red color. Okay, in alkaline solution, the alkali will react with the H plus to form water. Will remove the H plus, therefore the position of equilibrium will move to the right. Okay, so the color of the indicator in alkali will be yellow. Yeah, so it's similar to like phenolphthalein, when you it's colorless and it's pink. So those are the two extremes. Yeah, so methyl orange, the two extremes are red and yellow. When it's in acid conditions, it's red. When it's in alkaline conditions, it's yellow. When it's the end point, it'll be the mid color, which will be orange. Okay, so because indicators are weak acids, indicators have got different Ka values. Because they're weak acids, have different Ka values. Okay, so but if you think about it, Ka is H plus, concentration of H plus, times the concentration of A minus over the concentration of HA. At the end point, at the titration end point, concentration of the acid equals the concentration of the conjugate base. So they can cross out, they equal each other. So Ka equals H plus, therefore minus log Ka equals minus log H plus. Therefore pKa equals pH. Remember the P just means minus log. Okay, so the indicators, they change color over pH range. Okay, so it's not kind of quite a sudden thing. The indicators change color over about a 2 pH unit range. Indicators change color over a range of about 2 pH units, Okay, but when you're working out which indicator to choose, pKa at the endpoint, pKa equals pH. Right, what would you actually be asked to do in an exam question? All right, in an exam question, you'd be asked to sketch the titration curve. You'll be asked to choose the indicator, and then you'll also be asked to do some calculations on the titration curve, right? So let's do some sketching first. So I'm going to do there's four different scenarios, okay? So I'm sorry, you just have to bear with for a second. All right, so if we have pH, right, and I want to get all the way up to 14, so not to do too big, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, okay? And each time we're starting with the acid in the conical flask, okay? So if we have a titration curve that starts at about pH 1, okay, and then finishes at about pH 13, okay, that is a strong acid, strong base titration. So for example, something like hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base, okay? So that would be a strong acid, strong base titration. If we did another titration curve, okay, the same scale, right? So this time the pH starts at about pH 4, but finishes at the same point, about pH 13, then that is a weak acid and a strong base. So that would be something like ethanoic acid and sodium hydroxide. Okay, so and then the other combination, we've got strong acid, strong base, we've got weak acid, strong base. So the other combination, so we just draw another axis again. So the other combination, so there's one, I'm just going to do the axes 2, 3, 4, 5, 6, 10, 11, 12, 13, it's on your sketch, 14. You could be asked to plot it, but in exams you'll be asked to sketch it. So the other combination is if we start about a strong acid, but this time it's a weak base. So a strong acid about pH 1, but then we neutralize about, it finishes, at about pH 9, yeah? So about pH 9 approximately. So that will be a strong acid, something like hydrochloric acid, with a weak base. So that will be something like ammonia. Okay, and the last combination, so we've got strong acid, strong base, weak acid, strong base, strong acid, weak base. The last combination is a weak acid, weak base. Okay, and that's the worst combination, weak base. So something like ethanoic acid. This is when you're doing a titration, and ammonia. So you'd start at about pH 4, you'd end at about pH 9, okay? And the problem with this titration curve is that there isn't a sharp vertical. There's like a little vertical, and then it, okay, that's not very good. Okay, let me do that again. There's like a small vertical, it's just not a very good vertical, okay? So there's no sharp vertical on this one. And when we say there's no sharp vertical, what's happening on the vertical axes is one drop is being added, and then neutralization is happening, and the pH increases quickly. Right, So they'll give you, in an exam question, you'll be given some indicators. So I've written some out here. I don't know if you can, I don't know if this is, you can see this very well. You'll be given different indicators and the pH range at which they change color. Okay, so where the end point happens. And you need to choose which indicator to use for which titration. Okay, now if we look, for example, at the weak acid, okay, if we look at the weak acid and this one here and the strong base, and if we look at the indicator thymol blue changes color from 1.2 pH to 2.8 pH. So thymol blue would change color down here. Okay, neutralization happens about there, pH, I don't know, about pH 8 or something. Neutralization is happening. Thymol blue would change color before the neutralization, so you would not get the equivalence point. You wouldn't see when the volume of solution equals each other. You couldn't use thymol blue in this example. Okay, bromophenol blue changes color 3.6 to 4.6. Well, that's a bit dodgy as well, because that will change color around here. See, that's still no good. You want to choose an indicator. Ideally, you want to choose an indicator that changes color near the equivalence point. Changes color near the equivalence point is the best indicator. Okay, one that changes color near the equivalence point. So what we say, the kind of official way we say it is we say that the color change of the indicator, I'm just going to write it at the top, yeah? The color change of the indicator, coincides with the vertical section of the pH curve. That's what you need. Okay, the color change of the indicator to coincide with the vertical section of the pH curve. So you want an indicator that changes color around pH. This is like 6 to 8 around there. Okay, so the best one actually that you would choose in the case of a weak acid strong base, the best one you would choose is metacresol blue. Metacresol purple, because that changes color 7.4 to 9, and that will coincide with the midpoint of the vertical section. Okay, now you'll be given a table of indicators and asked to choose an indicator. Choose an indicator the color changes in the midsection. There are two indicators that you need to know even without a table, right? You should know the indicator phenolphthalein. Now phenolphthalein changes color high up. It changes color approximately pH 8 to pH 10. Okay, phenolphthalein changes color. It starts at pH 8, it'll be colorless. Up to pH 8, it'll be colorless, and then towards pH 10, it becomes pink. Okay, if this is the equivalence point of a strong acid and a strong base, phenolphthalein is still okay. You can use phenolphthalein as the indicator. The other indicator you need to know is methyl orange. Methyl orange changes color lower down. Okay, it's about 3 to 4 around there, methyl orange. Okay, as we've already said, methyl orange, when it's in alkali, it's yellow color, and when it's in acidic, it's red. Yeah, so methyl orange is okay as well, but ideally you want an indicator that changes color right in the middle. But if you are doing a strong acid and a strong base titration, you can use either phenolphthalein or methyl orange, because the color change happens on the vertical section of the pH curve. Okay, so you won't miss the equivalence point, the end point. So these indicators have got different pH values because they've got different Ka values, because they are weak acids. Right, if you take, so either of these, they're both good, yeah? If you take the weak acid strong base, methyl orange changes color down here. There's methyl orange. Sorry, methyl orange. That's too low. That indicator would not be a good indicator for a weak acid strong base. Phenolphthalein, however, would be a good indicator. That would be all right. Phenolphthalein would be a good indicator. If you look at the strong acid weak base, methyl orange changes color down here. So on the one drop is added, and then it changes color. That would be good. That's okay as an indicator. Whereas phenolphthalein is too late. Phenolphthalein changes color up there. Phenolphthalein changes color up there. That is too late. That's no good. Okay. Spelling of phenolphthalein. Phenolphthalein. Okay. So that would be not a good indicator. Methyl orange would be a good indicator. For weak acid, weak base, there are no suitable indicators. And there's no suitable indicator when you're doing this titration, because there is no sharp vertical. Okay, so there's no suitable indicator.